last lecture we discussed a very interesting concept called principal axis of rotation. So, let us start today's lecture by considering an example. So, again we take the same example of this rectangular prism of mass m with different sides A, B and C. Now, it is given that A is equal to 3C and B is equal to 2C, and the question is that to determine the principal moments of inertia and the principal axis of inertia about the origin O. So, again the same origin at the corner and the x, y, z axis at the sides of the prism. Now, given this system, we have already calculated the, in one of the earlier example, we calculated the components of principal axis, the moments of inertia. So, let us recall that we got the Ixx to be 1 by 3 m b square plus c square, and Iyy to be 1 by 3 m a square, sorry, c square plus a square. So, now this b is equal to 2c. So, this will be, so we can take the mc square outside and this will be 5 by 3, and Iyy similarly a is equal to 3c. So, this will be mc square times, so 10 by 3, and Izz was 1 by 3 m a square plus b square. So, this will be m c square times, so 9 plus 4, 13 by 3. So, this was the components, and the products of inertia were Ixy was 1 by 4 m a b, which is, so this is 3 and this is 2. So, this is m c square times 3 by 2. Iyz was 1 by 4 m b c. So, this is m c square times, so this is 2 by 4, which is half, and Izx is 1 by 4 m c a. So, this is m c square times, so a is 3c, so 3 by 4. So, then we can write down a moment of inertia tensor, a matrix, which is the first diagonal terms are Ixx, Iyy, Izz. So, this is, I am going to take this m. So, remember I am going to write it here. So, I am going to represent it as a matrix. Then we have xy terms, and this is a symmetric matrix. So, this is Iyx, which is symmetric, same as Ixy. This is Iyz terms. So, by symmetry this is Izy is Iyz, and this term is Izx, which is same as Ix zx. So, now for all the terms mc square part is common. So, the first part is 5 by 3, second yy term is 10 by 3, third term is 13 by 3, xy term is 3 by 2, yz term is half. So, and zx term is 3 by 4. So, then by this is the 3 by 2, this is half, and this is 3 by 4. So, this is the matrix moment of inertia in a matrix form that we have determined in this particular choice of reference frame. So, the question is to sort of diagonalize this matrix. So, diagonalize this matrix. So okay, so this, so I am going to write the, so first thing is will be 5 by 3, 10 by 3, 13 by 3, then you have 3 by 2 and 3 by 4. So, this is 3 by 2, 3 by 4, this is half, this is half, minus lambda, minus lambda, minus lambda equal to 0. So, this goes up. So, this gives us the eigenvalue equation, the lambda, and there will be 3 possible choices of lambda, 3 eigenvalues, because in 3 dimension we have 3 possible axes of rotation corresponds to 3 possible moments of inertia about 3 possible axes. So, these are the 3 eigenvalues, and once we get the eigenvalues, then step 2 is to get the eigenvectors. So, in general these eigenvectors will give us the directions. So, if I take the eigenvector of unit magnitude, that will give us the direction of the principal axis of rotation. Now, this diagonalization, nowadays there are standard ways. So, you that you learn in your mathematical methods course or in some computational analysis course. So, I ask you to complete this calculation and find out the eigenvalues and eigenvectors, and the eigenvectors of this, once you find the diagonal matrix, that will represent the eigen directions, and those will give you the direction of the principal axis. Now, we go to, now with this background, so far we have some background. For an extended object, we have computed 2 properties, that even though we have an extended object, if I still want to represent by some representative point, that will be the center of mass, and how to locate the center of mass. This is something we have discussed. And then we said that when we talk about rotation of a extended object, we need another quantity which sort of represents the extent of mass distribution about the axis of rotation, and that is the moment of inertia. With that background, now we are ready to do the physics part, which is that to describe the rotational motion of a rigid body. Now, here is a picture in which I showed with example some possible types of motion which are allowed for a rigid body. So, for example, we have a translation along a straight line in which the magnitude of the direction of the motion is constant, and this motion is possible both by an extended object as well as a point mass. Second example is a translation along a curvy path. For example, it could be a circle. In this case, the direction of the motion can also change. For example, in the circle it is continuously changing. This is also a motion that is allowed for a point mass as well as an extended object. So, these are translation. The third type is a rotation, and in the simplest case we have a planar rotation or a fixed axis rotation. So, we have a axis of rotation which is fixed, and the body, and let us assume that the axis of rotation is passing through the object, and then so this is rotating about itself. So, this is an example shown here like a compound pendulum. So, this is something that point mass cannot do, because a point cannot rotate about itself. So, this is what the difference between an extended object and a point mass. And then we can have a more complicated motion which is a combination of translation and a fixed axis rotation. So, this is called a general plane motion. Plane because if you take one point and you draw its trajectory with time, you will see that it moves in a plane. So, here is an example of a mechanism which is called the crankshaft mechanism. So, here some part is rotating and the rest other part is translating. So, we took this example when we discussed the principle of virtual work and constant motion. So, but this is also an example where you have a combination of translation and rotation. Now, translation versus rotation, what are the similarities and difference? Now, in mechanics you can essentially ask two questions about the motion. The first question is that how do we describe the change of position with time, and for that, in the case of translation, we use the displacement. We can monitor the displacement of an object, and then how does the rate of change of displacement, which is the velocity, and the rate of change of velocity, which is the acceleration. Now, for the rotation, instead of displacement, we monitor the angular change, the change in angle, and we monitor the rate of change of the angle, which is given by the angular velocity, and similarly angular acceleration. The second question is that what is the cause of that change in position? Why the object is changing position? How do you explain that? And this requires the laws of motion, and here one important quantity that every object has is something called inertia, which in the case of translation, the important it enters as a mass of the object. In the case of rotation, it enters as a moment of inertia in the laws of motion. And in this case, we know the momentum principle that says that the cause that is changing the position is the force, and the effect of force or the external force on our system, the effect of force is to change the momentum. We can have an analogous quantity here. So, in the case of rotation, the quantity analogous to momentum is angular momentum, and the cause of change of angular momentum is the torque. So, we are going to discuss the relation between these quantities in some more detail. However, before that, I want to sort of put it as a side remark as some example of motion that we are not going to consider in this course, because in this course we are assuming that our extended object is a rigid body. But if in real life we often see objects that are extended but not so rigid. Here is a very famous example of a falling cat. So, it's an you can go to YouTube and find several videos where the show of experiment that you take a cat and take it hold it upside down in this particular position and then release it from some height. It most of the time or almost always lands on its feet. So, it sort of turns in air and lands on feet. So, the puzzle in this case is that if you release the cat from rest, then its angular momentum is not rotating. So, if the cat was a perfectly rigid body, then it is impossible to turn itself. But the cat is actually not a perfectly rigid body, it is an elastic body and different parts can deform with respect to each other. So, this particular phenomena of turning of the cat is called a zero angular momentum turn, and instead of going into more details, I refer to you some link on the YouTube where you can see some real actual experiment with falling cats and the explanation of the interesting physics behind it. But in this course, we are not going to take those kinds of objects. We are going to take extended objects which are perfectly rigid. So, our plan is to first recap some basic concepts that we sort of described here. So, that we are going to critically review these concepts and their relation between them. So, we start with the angular velocity. So, first let us say that we are considering a simple situation about rotation about a fixed point, pivot point. Now, the first thing is that if our system is a point which is one dimensional, then in 1D there is only translation, no rotation. So, in a perfectly, if we lived in a one dimensional world, there would have been nothing like a called a rotation, only translation. Now, let us say, imagine what happens in 2 dimension, like this disc. So, the disc is rotating. In 2 dimension, all rotations take place in that plane, a 2 dimensional plane. Some object, some mass is rotating, an extended object which is living on the plane, or a point which is living on the plane. So, all the rotations is happening in a plane, like for example, a circle or in some complicated shape. Then it is possible just to have level. So, the axis of rotation is always perpendicular to the direction of the plane. Hence, you can describe the rotation just by its magnitude, the speed. The direction of the rotation is always fixed, is always perpendicular to that plane. There is no other possible choice. So, so you can pretend that the angular velocity is just a magnitude. So, how to describe it? So, first we identify the axis of rotation such as the one shown here. Then the vector, consider a vector whose magnitude is the angular speed omega and its direction is along the axis of rotation. So, remember that axis of rotation by definition is fixed. So, the direction is fixed. Now, there are 2 possible direction, the up direction and the down direction, and you can choose which direction by applying the right hand rule convention, that you curl your finger, right hand finger in the direction of the rotation or the spin, then the thumb points to the, so the thumb points along the axis of rotation and its direction is the direction of omega. So, in this case the direction is kind of fixed and the only thing that matters is the magnitude. Now, in our actual real world, the 3D world, there are 3 possible independent planes. So, the crucial word is independent. So, the rotation, in order to describe rotation, we have to take not a single plane, but 3 possible independent planes. So, each of these planes can be, the orientation can be specified by the direction which is normal to the plane. And as we know that in 3D there are 3 possible independent mutually perpendicular direction, hence the rotation takes place in 3 independent planes. So, you have to specify the angular speed in each of those planes. So, there are 3 planes, so there are 3 possible angular speed. So, that means we can sort of guess that in 3D the angular velocity, to describing the angular velocity, we need 3 components in the most general case. So, that sort of tells us that angular velocity is a vector. Now, to be precise, the angular velocity is technically, so it behaves in the same way as a vector under coordinate transformation, but it behaves a slightly different way under a reflection. So, under a rotation it behaves same way as the position vector, but under reflection it behaves in a slightly different way. So, this technically speaking, this is called a pseudo vector, not a vector, but both pseudo vectors and vectors, they have magnitude and direction. So, for our purpose there is no distinction between a pseudo vector and a vector. Now, to define formally the angular velocity, we say that given an object which is rotating with an angular velocity omega, now we know that the speed of the angular speed is the magnitude and the direction given by the right hand thumb rule along the axis of rotation is its direction. Then it is related to the linear velocity, the velocity of the particle, of a point particle, the velocity of a point at a position r. So, let us say this is our origin and this is a point which is rotating with some particular in 3D, then this direction of this point, the position vector of this point is r, vector r. So, this is boldface, means this is a vector quantity. Then its linear velocity, the actual velocity v, which is the rate of change of displacement and is related to the position vector, the location, by this particular expression. You are familiar with this, perhaps you are familiar with this expression in the magnitude, which is a 2-dimensional version where we only need to consider the magnitude, but in full 3D we need to describe it as a full vectors using the full vector notation. So, the linear velocity is the cross product between the angular velocity and the position vector. So, that defines the angular velocity. Now, here is one important point to note, that angular velocity is defined for a given reference frame. So, you have to specify the reference frame when you specify the angular velocity. So, for example, suppose, so this is also true for linear velocity, you have to specify when you say a car is moving or with a speed 60 km/h. So, you are basically saying that the car is moving with respect to a reference frame of the road, but if you are sitting inside the car is actually not moving with respect to you at all. So, this is also true for angular velocity. For example, if you have 3 coordinate system or 3 reference frames S1, S2 and S3, let us say that all of them has the same common origin, then S1 is rotating with an angular velocity omega 1, 2 with respect to S2, and S2 in turn is rotating with an angular velocity omega 2, 3 with respect to S3. Then S1 rotates with respect to S3 with an angular velocity which is the sum of omega 1, 2 plus omega 2, 3. So, this is like addition of velocities. So, the angular velocity is always relative to a particular given reference frame. So, let us try to take an example to understand this. Here is a sphere which rotates. So, there is a sphere, this is a sphere, and there is a stick, this is a stick which is initially pointing in the z direction as shown in the left figure, and this sphere is rotating about this particular stick with an angular speed w3. Now, what you do is that you grab this stick and then you start rotating this stick rotate it around the y axis with angular speed w2. So, this is the stick which is now rotating about the y axis, which is with a speed w2. Then the question is, what is the angular velocity of the sphere with respect to the lap frame? So, just to in our notation that we used earlier, so this w3 along z hat. So, w3 along z hat, this is the angular speed of the. So, there are 3 frames, the frame of the sphere, the frame of the stick and the lap frame in which we are observing. So, w3 is the angular velocity of this sphere with respect to the So, the angular velocity of the sphere with respect to the stick, and omega 2 which is shown here, this is omega 2. So, the stick is now rotating about x axis about y axis. So, that direction is along the y axis, which is the axis of rotation. So, the angular velocity of the stick is, so you take, so this is, let us say this is our z axis and this is y axis. So, you are starting to rotate this stick about this direction by hand, and the sphere is moving around the stick in this direction. So, the angular velocity of the stick with respect to the left frame is omega 2 y hat. Then the by what we learned so far about the addition rule of the vector, the relative velocity. So, the if you want to know the angular velocity of the sphere in the left frame, this is now doing a complicated motion. It has two rotation, one is rotation around the stick and plus the rotation of the stick in around the y axis. So, the net angular velocity of the stick is now omega 3, which is the sum over omega sum of the angular velocity of the stick plus the angular velocity of the sphere with respect to the stick. So, now it has two component. So, the direction of the angular velocity of the sphere is now along this particular direction. So, it is now doing some sort of a complicated motion. Now, let us come for the sake of completeness, let us point out put a brief remark about the how to derive this relation. So, I am not going to derive it give you the proof, but I just want to point out the basic logic by which we can deduce this particular relation is that. So, we can start with this notation rule that V is equal to omega cross r, and then for the V, the linear velocity, you apply the relation for the linear velocity, they will just add, and then you apply this relation, and then you can show that this particular, you can deduce this particular relation. So, just to summarize, today we reviewed a basic concept for describing rotational motion, which is the angular velocity, and the angular velocity in 3D in the most general case is a vector with 3 components, and its direction is along the axis of rotation. In the next lecture, we shall review the relation between the angular velocity and angular momentum, and there it will be clear why the moment of inertia is not a simple scalar quantity, it has to be a matrix. Thank you.